So, new stuff, minor losses, okay? We know with a pipe system, pressure drop is caused by friction, okay? Frictional effects in the pipe, okay? And the friction that we've mostly been dealing with recently is the friction between the wall of the pipe and the fluid that's flowing in the pipe. Now, there are many other components in pipe systems, okay? We've all been dealing with a very simple straight pipe. Can anybody think of a common component in a pipe system? Okay? A bend, exactly, a bend. Other things, anybody? A junction? Tapering, yep. Change in section, okay. There's also all sorts of other things. We covered last semester, we looked at flow rate measurement devices. There were orifices, okay. That's the thing in the pipe. And there are all sorts of other things. And so bends, as we said, entrances to pipes, exits of pipes into reservoirs. We've got section changes. So you're running on a pipe of 22 millimeters. It suddenly increases to 38 millimeters. There's a pressure drop associated with that. Junctions, okay, so we've got two pipes joining into one. Filters, okay. And of course the big thing is valves. And valves we put in pipes to give us a deliberate pressure drop, okay. When we want to turn the tap off, okay, that's a valve. And you want to slow the pressure of the water coming out, you turn the valve down, that causes a pressure drop. And that's exactly what's going on here, okay. And so valves, you get a value that will influence how much the pressure drops are, okay? Now each of these things here, bends, entrances, exits, okay, they're all known as minor losses, okay, and they all contribute to a pressure drop, okay? How do we work these out? Well, what we do is each of the components has a loss factor, which we call K, okay? Essentially, it's a bit of a fudge factor that we stick into our Bernoulli's equation, and it gives us an approximate pressure drop, okay? So this is due to pressure, okay? And it's very similar form to this, except for instead of FL upon D, we drop that, and we insert K. So we've got K times the dynamic pressure, okay? K being our loss factor. And on page 28 of your notes, we've got a list of typical components, okay? And for each of those components, I've given you a K factor. Okay? Sorry about the quality, but we had to copy this from an old set of notes. And you can see we've got things like a section increase, okay, a section decrease. Then we've got an orifice, which you've all seen before, okay. We've got a taper, an enlarging taper or decreasing taper, a bend, a curved bend, various other sort of things as well, okay. And there are K factors. Sometimes it's just a value you pick. Sometimes you've got to determine it from different areas, okay. And then that table in the corner is a bunch of different fittings and typical K factors. You notice with the valve, okay, a globe valve, fully open, has a K factor of around 10, okay? So that's a big pressure drop just because of the valve in the system, okay? And you'll see, another example of a valve is the butterfly valve in a car engine, okay? You've got your intake, looks something like this, okay? And generally in a car engine, you've got a valve that looks like that. And then depending on the angle, okay, that valve opens or closes. And of course, when the valve is fully open, okay, there's still going to be a pressure drop because you've still got something in the system, which is why, if you look at Formula 1 cars, okay, they've got valves that operate at the side. And so it's like this, okay, oops, let's go like that. Okay, and when the valve is fully open, these rotate in to the walls, and you end up with nothing in the pipe, okay? And obviously you get full flow through there. There's no pressure drop associated with the wide open throttle in a Formula 1 car engine, okay? But with your car engine, petrol engines, you'll get a pressure drop just because there's a throttle valve, okay? So, now, if you've got more than one loss in the system, say you had a couple of bends, you've got a valve, you've got a filter, okay, then there's going to be a K factor associated with all of these things. And what you need to do is you just add them all together, okay? The sum of the effective K factor, which I've given the subscript E, okay, is basically all the K factors added together. And you just get the sum from I equals 1 to n of K. That should be Ki, not Kn. Okay? And so you end up with this equation. Delta P is K plus 1/2 rho c squared, okay? And we know that K is the sum of all the K values, okay? So 1/2 rho c squared. Like I said, this should be an I, not an N. That's a mistake. Apologies. So, the total pressure drop, okay? Friction effects with the wall still haven't gone away. They're still there, okay? So what we need to do is we need to add them together. We've still got the pressure drop due to the friction, okay? And we've also got the pressure drop due to the minor losses, okay? That's minor losses there. And so you add them together. Well, here's our minor losses, okay? Here's our one due to friction. Notice we've got a common term here, 1/2 rho c squared. And so you can simplify it by saying that the pressure drop, delta P or delta PL, if you've got a pump in the system, is simply the sum of all the minor losses plus the friction factor, or the friction term, okay, times by the dynamic pressure. And so you can now stick this term into Bernoulli's equation, which will give you the response. In summary, come on guys, 2 minutes. Oh, whoops, wrong one. There we are. Okay, has everybody got it? Yeah? Okay, right. Okay, so in summary, we've reviewed turbulent flow. Okay, we looked at how you determine the friction factor. Okay, using the Moody chart. I hope you've all managed to suss that out now. Obviously, we're here during the tutorials to help you out. Okay, if you still need to work it out. We cover minor losses, which are essentially factors that we can introduce into Bernoulli's equation to determine what the pressure drop is associated with various different components. These components and pressure drops we call minor losses, okay? Additional losses in pipe networks, and they can be quite considerable, especially if you're dealing with a valve, okay? And a valve that's fully open, okay, can have a K value of, say, 10. Guys, come on. Okay. The losses in a valve can be quite considerable. We have a globe valve in your list that has a K value of 10, okay? If that valve was, say, half closed, that pressure drop suddenly shoots up by a factor of 10. The K value would be 100, okay? They can be quite considerable valve pressure drops, okay? And for good reason. We like them, okay? We use them all over the place to reduce the pressure in the system. And so the total pressure drop continued based on last week's pressure drop due to wall friction. We've now got this extra term, the effective K value, okay, which is the sum of all the K terms, plus your FL upon D times by the dynamic pressure. And that's your pressure drop in a turbulent pipe system, okay, with minor losses.